So yep, over here they used that strategy. They split it into two to make it more obvious that you can utilize this formula here. So let's find the indefinite integral. So that's the typical anti-differentiation of 4x to the power of 5. Now, my instinct, again, is not to use that formula. It's just to think, okay, it must have been x to the power of 6, which means if you derive x to the power of 6, it would become 6x to the power of 5. So then there must be it must be 6 over, it must be 4 over 6 x to the power of 6. And the reason is because if we derive this, we will see, okay, there is a 6 multiplied by our 4 over 6 multiplied by our x over 5, which equals to 4, not x over 5, sorry, x to the power of 5, which equals to our 4x to the power of 5. So that would be my instinct, and I know a lot of students do it like that. They just sort of look at it and they can feel out what must create it. They're sort of doing, they're sort of reversing the process a little bit. They're finding out how to create this value here as opposed to applying any formula. What would you derive to create this? Therefore, what does this anti-derive to? On the other hand, let's also utilize the formula to do it because that is a more consistent, reliable way. So we have 1 over, and n in this scenario is 5, so 5 plus 1 multiplied by x to the power of 5 plus 1 multiplied by, plus c. So in this scenario, we have, we actually have to multiply this by 4 as well. I do make that mistake a little bit. One thing that's actually very important to note that could help you just understanding this is, since constant values basically are kept out the front during anti-differentiation and differentiation, this here is equal to this. So we can, if we're able, we can remove a common constant value outside of the equation, which can make it easier for us to look at. So it's easier to apply this formula here. So if there's a 3 here, you can just move 3 outside. And that makes our goal a little bit easier. So yep, we don't want to forget this 4. We have this constant value 4, and then we multiply it by our formula here, and that is equal to 4 over 6 x to the power of 6 plus c. And if we move 4 outside, we could have it like in brackets as well, everything in brackets. So the 4 gets multiplied by everything, but again, we don't write 4c because c just represents any possible value. So 4 times any value includes any value, so we can just keep it at c. So let's utilize the formula for 7x to the power of 13. Is equal to 7, so we have our constant value that we shouldn't forget, multiplied by 1 over 13 plus 1 multiplied by x 13 plus 1. Always remember to add that c on the end. So that is 7 over 14. Now this is actually a mistake up here. I've forgotten to simplify it a little bit. Fractions, you should always try to simplify it, and we have to do the same over here as well. Multiplied by x 14 plus c. So that's equal to 1 over 2 x to the power of 14 plus c. So we'll rub all this out just to give us some space for the following questions. So this one's a little bit harder because we're not looking at numbers, we're looking at representations of numbers. So we assume a and b in this scenario. We're going to assume that they're some constant value. So we're differentiating a multiplied by x squared plus b multiplied by x. Now the first thing that's good to do if we're going to utilize this formula is we separate these terms into their own anti-differentiation sort of sets. So we have bx. Now another thing we can do is we know that we're assuming a and b are just these constant values because that's the type of question you get in Unit 3. So we are going to move a out the front to simplify everything for us, and we're going to move b out the front for both of these integrations. So now what we can do is we can utilize this formula for each of them. So for the one with a out the front, we have 1 over 2 plus 1 multiplied by x 2 plus 1 multiplied by a. And then we have to add our second term here. So that is 1 over 1 over 1 plus 1 multiplied by x, 1 plus 1 as the power there, and then all multiplied by b. So that should be equal to a on 3 times x on 3 plus b on 2 times x to the power of 2. Okay. So lastly, we have this one here. Now we'll try to apply this formula. Just consider that 1 over x to the power of 2 is the same as x to the power of minus 2. So let's do this. We're going to integrate 1 over x to the power of 2. Now that's equal to x to the power of the integral of x to the power of negative 2. So from here we can apply this formula all the same. And this formula might even be a little more useful when you're working with like you have a negative power, because it's just a little harder to look at. So this is equal to 1 over minus 2 plus 1 multiplied by x minus 2 plus 1 plus c is equal to minus 1 I'm going to do times x minus 1 there plus c. So that is minus x to the power of minus 1 plus c. And hopefully that is all correct. I could have made a mistake, as you do, but I think generally that's the idea that we're going with here. Some of these you can look at them and you can see sort of patterns that you would expect. For example, I can see that, okay, the power here will become to the power of 14, and then to get the 7 out the front, that must necessarily mean that I have a 7 over 14 at the front. So those are some patterns that we have. That you can use instead of using this formula when you get this specific formula here, when you get really comfortable with these basic integrals, especially when you're moving between differentiating and anti-differentiating so often, you will start to see just the general patterns there. Now, this is very important. Don't forget to add the plus c. I know that's a big problem that I had during my time in grade 12. I would very consistently forget to add that plus c, which is extremely important, obviously. Otherwise, you're missing a value, especially when you start doing multiple layers of integrating, because what you can do is you can have to do the integration of the integration. And like, let's say we had the integration of x, it would become, okay, now we want to do one level of that. So we have 1 over 2 x squared plus c, and now we integrate this as well. So then we have 1 over 6x to the power of 3 plus cx plus d, and d would be another constant value. So that's sort of what we're looking at here. That's why c is very important, because especially for multi-stage questions, because it remains consistently relevant when you have to do multiple levels of integration, which is actually quite useful for some real life applications, such as like for example, if you're able to make a line that represents the displacement of an object in physics, then if you differentiate that, you will get a line that represents the velocity of the object at any point. And then if you get the differential of that, it'll become the acceleration of the object. So there's many layers of differentiating to get real life applicable values. And then let's say you had the the acceleration, and you wanted to find the possible displacement. Then you would have to do 2 layers of getting an indefinite integral. So C is very important to keep, otherwise whatever you've written is not mathematically valid. So now we have definite integrals. So they give an actual number. They don't give a formula like an expression like we were getting here. So when we differentiated this, it wasn't a constant value. It's an expression. It's a function. Now we're going to get an actual number here because we're going to use these 2 numbers to evaluate something out of the function that we get. So I'll go straight into doing an example here. Here we're going to derive between these 2 points. We're going to get a definite integral between these 2 points of x minus 4. So first I'm just going to derive x minus 4 just to conceptualize this. So that will result in 1 over 2x squared minus 4x plus c. And we can see if we did derive, that would become this, and then the plus c would become sort of plus 0 on the end. It would become nothing. So that makes sense. Now, when we do the definite integral, this is equal to this. So we have our 1 over 2x squared minus 4x plus c. And we put these in these square brackets, and then we put our same numbers that we have here at the end of these square brackets because we still haven't used them yet. Now what we do is we substitute the first number in. So we go 1 over 2, the top number here, so that's 4 in this scenario, times 4 squared, minus 4 times 4, plus c. And then we do a negative, big brackets, and substitute the second number in. So 1 over 2 times 0, that's our second number, minus 4 times 0, plus c. So that's equal to 1 over 2 times 16 minus 16 plus c minus c. Now, whenever you're doing this definite integral, what you'll realize is if you start always doing plus c, if you start using the plus c, you realize that the plus c cancels out every single time. So with definite integrals, you don't actually even write the plus c because it's just mathematical knowledge that no matter what, that plus c will cancel out because you substitute the top number in, and then you subtract everything where you substituted the bottom number in. Which means since c has nothing substituted into it, it'll always be c minus c. The top number being substituted in will always have a c on the end, and the bottom number being substituted in will always have a minus c there. So we could even go through and we could just remove all instances of c existing in here. So this is what we end up with. We end up with 8 minus 16 is equal to minus 8. So that's our result. That's our definite integral. Now, the fundamental theorem, let fx be a function continuous in the closed interval, a is smaller or equal to x is smaller or equal to b, and let fx be a primitive of fx. So we're saying fx is the indefinite integral. So what we're doing is we're getting the indefinite integral and we're substituting in b, and then we're subtracting our substitution of a into the indefinite integral. So we can go back and sort of apply it in that way as well. We'll go back here and we'll redo some of this question by applying that sort of form instead of using these square brackets, which I think are more commonly used. So now we have, let's go all the way back here. Okay. So we will set this equal to fx, as is described over here. Now we will say, okay, therefore fx is equal to 1 over 2x squared minus 4x plus c. So now we have this over here with these definite values. This definite integral has f4 minus f0. So that becomes 1 over 2, 4 squared minus 4 times 4 plus c minus 1 over 2 x squared times 0 minus 4. That's my mistake. Go back here. That cannot be rubbed out. Okay, 1 over 2, 0 squared minus 4 times 0 plus c. And that should be all a minus out the front. And that should be a plus. Okay. So basically, that results in the same thing that we found before. So the square brackets are sort of a notation that I think is most widely used when you're just solving by hand, because it's just quite efficient. And you don't usually put the plus c in there. So definite integrals, you get the basic integral, and then you substitute b into it, and then you subtract the integral with a substituted into it, and that's your answer. You could ignore c, given that c will always cancel in that equation. Is that the same one we did? Yes, it is. Yep, so this is sort of the basic notation that we tend to like to use. And then we separate it into these separate sets of brackets. So yeah, do remember it's very useful that you can divide the integral up. When two things are added together, you can divide it into separate integrals, and then you can evaluate from there, which can make, integrating a lot easier, especially when it gets like complicated like this, all the way down here. If you can separate those, it will make your life a lot easier. So evaluate the following definite integrals. So we have our range here. We have from 1 to 4, 2x. So I might want to go back and represent something here now that I think about it. I think I've already been over this, but we should sort of take a little look at what this actually looks like. So what we're finding is we're actually finding the area beneath the curve. So if we put lines here, and we said this is A and this is B, and then if this was fx, then we would be finding this area in here. And that's sort of what this is actually useful for in when we're applying it. So let's do that. Let's find the area under the curve 2x between the points 1 and 4. So this line would look something like this, and then we have this point 1 and this point 4, and this is going to find the constant value, that is the area in between those 2 points under the line. So this is equal to, now we're going to put the integral without c in these brackets, these square brackets. And then we can evaluate those. So that is equal to 4 squared minus 1 squared. So again, I'm substituting 4 in, then I'm putting a minus there and substituting the 1 into that second instance. So that's 16 minus 1 is equal to 15 is our answer there. So that's the area in here on this line there. So now we're going to look at a much larger line. So this line might look something like, this. And now we're going to find the area between 1 and 2. So that would be, we would have a 10 times, we'd have some fraction at the front probably, multiplied by x to the power of 5. Now we know it creates 10 at the end, so there would probably be a 2 out the front here. So 2 times 5 equals 10. So if we differentiated this, it would equal this here. Then we have our range, our domain, 1 to 2 is equal to, we have 2 times 2 to the power of 5 minus 2 times 1 to the power of 5. So that's equal to 2 times 2 to the power, that's equal to 2 times 32, I believe, minus 2 is equal to 62 all up. Now lastly, here we have a much more complicated one that we could decide to, I'll rub some things out so we have the space to split this one up into multiple different parts. So first I'll just do the basic integral. Now you don't have to separate it into multiple separate parts if you find that too laborsome, but you can. So then the answer to this would be and now if we were to apply it to the, let's put a little, if we were to apply it into these brackets here, these square brackets, we would get rid of the c because that value we know is going to be cancelled out, so we don't generally write it into the brackets. Good to put brackets around the second part because it's very easy to start writing, and I've done this before, talking from experience. It's very easy to put this minus here and then start writing the second, the negative part of the integral, and then you make the mistake of not putting brackets down and just writing the first term, and only the first term actually becomes negative. So you will end up with an incorrect result. So it's good to put brackets outside, or if you're very good at doing this, you can just swap the sign of each term as you go. So yeah, some of these questions can be quite long and more laborious, but really a lot of these sorts of questions are just, I feel like they're put in exams just to allow you space to make mistakes, really, because that's a lot of what these exams are about, I guess, just seeing how often you'll make mistakes. So I'm going to expand the brackets here. So that becomes a plus. This becomes a negative. We'll just put that to, it'll become a plus actually, because there's a plus, but it gets multiplied by -3. So there's a lot of addition of fractions there, which there's no point in us spending too much time on. Obviously, if you had a calculator, that wouldn't be a problem at all, but otherwise you probably could just manually go through all of this and add these fractions, considering they're all only 3 and 2 as the denominator. So basically what we're looking at here is, again, final little recap on the idea, because I think some people have never actually seen it before at this point. Basically, we derive what's in here. We derive the function. Then we substitute in the first value as all the x's in the function, and then we subtract the function where -3 or the second value is substituted in. Saying first value and second value might not be the best idea, because some people consider this the first value and this one the second value. That's why you'll see often A and B. And the reason that actually is because usually when you're looking at the area on a line, the A will come first, the B will come there. So I'd say maybe A is actually the first value. So maybe it's better to say substitute in the top value and you subtract the bottom value. Substitute.